Okay, so we are doing Pascal's triangle. So why don't we go ahead and create one here that we can reference. So remember, what you do is you have the ones on the outside, and then when you get to 3, you start adding these two above. So 1 plus 1 is 2. You put the ones on the outside. 1 plus 2 is 3. 2 plus 1 is 3. And you can see we're getting this symmetry. Okay, 1, 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5. 10, 10, 5, 1. Okay. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 35, 21, 7, 1. One more here. 8, 28, 56, 70, 56, 28, 8, 1. So, what exactly do all these numbers stand for? So we have so this would be yeah, let's make sure we figure this out. We could, once we get this set up, we know what row this corresponds to in terms of combinations. So let's say we don't remember what we were doing, so let's try 3 things 1 at a time is 3, and 3 things 2 at a time is, well, it's 3 things 0 at a time is 1, and 3 things 3 at a time is 1. So when you have 0 or you have the same number, it's 1, and so you have the symmetry. So that means this has to be, this row is for 3 things taken so many at a time. This is 4, this is 5, this is 6, this is 7. So really it's whatever is the number in this first position or the next to last position is the one that is appropriate. Okay, so now we've got this. We're going to use it, and we're going to start with problem number 1. So problem number 1 says take 4 things 2 at a time as a combination. So we go here to the 4th row. This is 0 at a time, 1 at a time, 2 at a time. So this is going to be equal to 6. Now, I guess you can go either way. This could be 5. This is 4, 0, or it could be 4, 1. It doesn't really matter because the symmetry holds. So again, just want to come up with something we can remember. 0, 1, 2, 3, 4, 5. So we'll start 0 on this side and we'll just count. Okay, so that's number 1. Number 4 is 7 things taken 5 at a time. So we come down to the 7th row, 0. So now we're going to start here, 0, 1, 2, 3, 4, 5. So the answer is 21. And then we have number 7, which is 9. So I actually need one more row, unfortunately. What I'm going to do is I'm going to select all these. I'm going to group them together, and I'm going to shrink them a little bit. Okay, so there we go. I'm going to shrink them a little bit so I can fit one more row here. So we have 1, 9, 1 plus 8 is 9, 28 plus 8 is 36. That's 70, 84. Then we have 70 plus 56, which is going to be 126. And now we have reached our point of symmetry, so we can just continue to write down the numbers. So that's for 9. Okay, so number 7 says 9 things taken 2 at a time, combination. So here's the 9th row, 0, 1, 2. So it's going to be 36. Okay, what we got next? 10. Okay, 10 has this committee of 4 congressmen will be selected from a group of 7 Democrats and 3 Republicans. Find the number of ways of obtaining each result. So oh, okay. It's like we need to know more information, but we do. They give it in the problem. So it says exactly 2 Democrats, which also means exactly 2 Republicans. So they don't say it, but it's implied. So we have how many Democrats? We have 7 Democrats. We take 7 things, take 2 at a time, and then we do the same thing with Republicans. We have 3 Republicans taken 2 at a time. So now we just need to go over to our table. 7 things taken 0, 1, 2, 2 at a time is 21. 3 things taken 2 at a time, so we got 0, 1, 2, 3 is the answer, and so you multiply that out and you get 63. And what we'll do is we will keep this, and I will insert a page. Actually, I got it inserted in the wrong place. Okay. So now we're going to 13. We've got 8 fair coins are tossed. Find the number of ways of obtaining each result. So we have exactly 3 heads. So what we need to do is, so what's going on here? How many times are we tossing this thing? 8 tosses. So the tendency would be to say 8 things 3 at a time, which is the correct answer. But why is that relative to coin tosses? So you have, so I'm going to stop and just think about this for a second so I give it a good explanation. So the way you have to look at this is you have to think of 8 positions, which would be the 8 tosses. And what we're looking at is if we give those a letter, so we have this is position. We'll use letter A for the first toss, letter B for the second toss, and so forth. And what we're trying to do is come up with a number of ways that you can arrange 3 of these together. So let's say I pick, one possible combination would be A, B, C. So you'd have a heads here, and you'd have a heads here, and you'd have a heads here. And then the rest, by default, would be tails. So another possible combination would be C, D, E. So then you take these and you would put them you put them here, C, D, E. Now, another possible arrangement of this would be E, D, C, but it would be the same three positions. So by doing that, you can write it as a combination. You've got 8 slots that you can stick the heads in, and you're putting them in at 3 at a time. Now you could do the same thing for tails. You'd have 5 tails. If you do 8 things 5 at a time, you'll get the same result. So you can either put the heads in certain locations or the tails in certain locations. So if we go over to Pascal's triangle, this is the 8th row, and we count 0, 1, 2, 3, so this is 56. Or we can go 0, 1, 2, 3, 4, 5, which is also the same thing. So let's just do one more in this group. Let's say 16. It says exactly, these are all exactly 6 heads, which is the same as 2 tails. And so in terms of combinations, you'd have, again, 8 slots, and you'd have 6. And if we go back to our diagram here, here's the 8th row, 0, 1, 2, 3, 4, 5, 6. So you get 28 for that. Or you could base it on tails, and you'd have 8 things taken 2 at a time. And so we go to our row 0, 1, 2, which is 28, same thing. So whether you do it in terms of tails or in terms of heads, you get the same result. Okay, and then the final 2 problems. Over the years, many interesting patterns have been discovered in Pascal's triangle. We explore a few of them in exercises 31 through 37. So 31 says, choose a row whose row number is prime, except for the ones in this row. What is true of all the other entries? For the table 5. Okay, so let's go to table 5. It says, choose a row whose row number is prime. Okay, so except for the ones in this row, what is true about the other entries? Okay, so let me delete these pages so we can look at, or actually let me move this Pascal's triangle here, and we'll try to make some observations about things. So 3 is a prime number. So if you don't look at the 3's, so you have row 3, you got 3 and 3. Okay, the next prime number is 5, and you have 5, 10, 10, 5. And the next prime number is 7. You got 7, 21, 35, 35, 21, 7. So one thing I noticed is these are all divisible by whatever prime number it is. So 3 is divisible by 3, 5 and 10 are divisible by 5, and 7, 21, and 35 are all divisible by 7. So that would be my observation. So let's see what the book says, if that's what they're looking for. It's problem 31. All are multiples of the row number. Okay, so we got that one. (31)B. Choose the second prime row number to see if the same pattern holds. Yes, okay, it does. Well, 7 was the, we'd have to go to 11, which I don't have enough. I didn't write it there. Using the user method to construct row 11 in table 5 and verify that the same pattern holds in that row. Okay, so let's, again, we're going to have to make this thing smaller. Okay, so we got 1, 10, 45, 120, use my calculator now. 126 plus 84 is 210. 126 times 2 is 252. And now everything's symmetric. 210, 120, 45, 10, 1. Okay, then we'll finally go to 11. 11, 55. 55 is divisible by 11. 120 plus 45 is 165. So it's 165 is divisible by 11. Yes. 210 plus 120. 310 plus 120 is 330. Yep, that's divisible by 11. And the final one, we don't have to go all the way across. 210 plus 252 is 462. Is 462 divisible by 11? Yes. Okay. So yes, that particular thing works every time. I shouldn't say every time, but it works up to 11. And the final problem is 34. It says construct another triangle by replacing every number in the Pascal's triangle, rows 0 through 5, by its remainder when divided by 2. What special property is shared by rows 2 and 4 in this new triangle? Okay, so we're going to create a new triangle. Take that out of there. That was the problem number. Okay, so let's read this in. Construct another triangle by replacing every another by its remainder when divided by 2. Okay. So the outsides are all 1s because 1 divided by 2 is, you get 0 plus a remainder of 1. Okay. 2 divided by 2 is 1. There's no remainder in this case. 3 divided by 2, basically if it's an odd number you have 1s, and if it's an even number you have 0s because there's 0 remainder. And let's go one more here, row 5. So this was, then you get 1, 0, 0, 1. Let's do one more just to see what happens. So you get 1, 6 is even, so you have 0 remainder. 15 is odd. 20 is even. And then it repeats itself like this. What special property is shared by rows 2 and 4? Okay, so row 2 is this one, and 4 is basically has zeros in the middle. That's what it looks like to me. Let's see what it says. Rows 2 and 4, every entry except the beginning and ending ones is 0. This is because the corresponding entries in the original triangle are all even. Okay. Now if you get to 6, you don't have, it doesn't, it's not like every even one does it. If we look down at this row 8, row 8 is all even, so that those things would all go to 0. Let's just try this out. So this is row 7. And row 8 would be, so let's write the row numbers here. 1. Actually, I missed a row here, didn't I? So there's there and there. Okay, so that's row 1 is this one. It's row 2, 3, 4, 5, 6. Okay, yep, 5, 6, 7, 8. Okay, so row 6 is this. Row 7 are all odd, so it's 1, 1, 1, 1, 1, 1, 1, 1. And then row 8 is 1, because the outsides are 1s, but all the interiors are 0s. So you get 0, 0, 0, 0, 0, 0, 0. So the 8th row, I wonder whether the 16th, so if it's powers of 2 that ultimately are that way.